Hi, everybody. It's Professor Mitchell. We're continuing with Chapter 8 today, and today we're going to talk about Section 8.3, which is calculating a confidence interval for the mean when the standard deviation of the population is unknown. In the last section, we talked about how to do it when sigma is known. So when the population standard deviation is unknown, we substitute S, the sample standard deviation, in its place to calculate the standard error. So recall from chapter 3 that this is the formula for the sample standard deviation. If you're taking my class in this chapter, I don't mind at all if you use technology to calculate the standard deviation, either with Excel or with a graphing calculator. So remember the notation from this formula. X is this X bar, sorry, let me fix that. X bar is the sample mean. There we go. N is the sample size. And X sub I minus X bar is the difference between each data value and the sample mean. And this is actually one of two formulas that we talked about to calculate the standard deviation. But again, if you would prefer to use technology to find the standard deviation, that's perfectly okay. All right, so to calculate the approximate standard error of the mean, instead of doing sigma divided by the square root of n, you just do S divided by the square root of n. And your textbook denotes the approximate standard error of the mean by sigma sub X bar with a little hat over it, okay? So it turns out to do this kind of confidence interval, we're going to use the student's t-distribution. That's used in place of the normal probability distribution when the sample standard deviation S is used in place of the population standard deviation sigma. The t-distribution is a continuous probability distribution with the following properties. It is bell-shaped and symmetrical around the mean, just like the normal distribution is. The shape of the curve depends on a parameter called the degrees of freedom, df, which is just the sample size minus 1. So you'll see how that works when we get into the examples. Like any probability function, the area under the curve is equal to 1. The t-distribution is flatter and wider than the normal distribution. And the critical score for t-distribution is greater than the critical z-score for the same confidence level. And you'll see some examples of that coming up in just a minute or two. The t-distribution is actually a family of distributions. As the number of degrees of freedom increases, in other words, as the sample size gets larger, the shape of the t-distribution becomes similar to the normal distribution. And when there are more than 100 degrees of freedom, the t-distribution and the normal distribution are practically identical. So here's a picture of, you see the normal distribution here in green. And in black, you see a t-distribution with 13 degrees of freedom. And then in red, you see a t-distribution with 5 degrees of freedom. Okay, so you can see as the degrees of freedom get smaller, the t-distribution gets wider and flatter. All right, so here we compare some t-scores and z-scores. So for an 80% confidence interval, we talked, I guess, in the last section about how the critical z-score for that is 1.28. A t-distribution with 30 degrees of freedom, it would be 1.31. With 20 degrees of freedom, it would be 1.325. And at 10 degrees of freedom, it would be 1.372. And you can see the same thing for a 90% confidence interval, 95%, 99%. So notice as we increase the degrees of freedom, the t-scores are all getting closer to the z-score for that confidence interval. So just like in the last section, a confidence interval is going to have an upper confidence limit and a lower confidence limit. Those are calculated very, very similarly to how we did it in the last section. The only difference, well, what's the same is you start with X bar, the sample mean, and then you add and subtract the margin of error. So really the only difference is instead of using a critical z-score, you're going to use a critical t-score. And of course, you're going to replace the standard error of the mean with the approximate standard error of the mean. All right, so for example, a hospital manager wants to estimate the average number of days patients spend in the hospital for a surgical procedure. Suppose a sample of size n equals 15 has a sample mean of 5.11 and a sample standard deviation S equals 0.85. So notice sample standard deviation, and they've labeled it S. So that tells me that this is going to be a t-distribution problem and not a z problem like we did in the last section. So the population standard deviation has to be treated as unknown. And we want to calculate a 95% confidence interval for the population mean. So first we'll find, that really should say the approximate standard error of the mean. And again, instead of doing sigma divided by the square root of n, you do s divided by the square root of n. 0.85 divided by the square root of 15 comes out to be about 0.2195. Next, we have to find the critical t-value for 14 degrees of freedom. Remember, the sample was size 15. The degrees of freedom is always that number minus 1. So let me show you how to find this number in table A3. And if you're taking my class, I've got table A3 posted in the module with this assignment. Oops, I just noticed that whoops, okay. All right. That was basically what I wanted to do anyway. All right, so going down to 14 degrees of freedom, we're doing a 95% confidence interval, which means the area in two tails is 0.05, okay? So where that column and that row meet, you will see the 2.145, okay? So that's going to be the critical t-score for this confidence interval. All right, so now that we have the critical t-value, we'll calculate the interval endpoints. Remember, the sample mean was 5.11. So now we will add and subtract the margin of error, which is 2.145 times 0.2195. Remember, the 0.2195 was the approximate standard error of the mean. So we find that the upper confidence limit is 5.58 and the lower confidence limit is 4.64. So based on our sample mean of 5.11, we are 95% confident that the population mean is between 4.64 and 5.58 days. So as an alternative to using table A3, you can also find critical t-scores using Excel's t.inv.2t function, which has the following characteristics. You put equals t.inv.2t, and then the inputs for that function are alpha, the confidence level, and the number of degrees of freedom. So for example, to do the previous problem, you would enter equals t.inv.2t and in parentheses 0.05 comma 14. And Excel gives you this decimal with all these decimal places, and you can round that to 2.145. And that's going to take care of section 8.3. We'll see you next time.